some neighborhood operators. So filters. First, we should know why we need filters. Filters are essential components in image processing that will modify a signal or image by removing unwanted components such as noise, or we can enhance the certain features in an image. That is the purpose of filter. Okay. First one is linear filter. Linear filter is a filter that adheres to the principle of superposition and homogeneity. This means a superposition means if you input a sum of two signals into the linear filter, the output will be the sum of outputs. And homogeneity means if you scale the input, if you enlarge or shrink the input with some value, the output will be scaled by the same factor. In simpler term, we can say they don't introduce new frequencies which are not already in the signal. Some examples are Gaussian filter and mean filter. And the non-linear filter means it will introduce some new frequencies into that component. So some examples are minimum filter, maximum filter, and median filter. And the next one is semi-global operators. Semi-global operator means it will not look at the entire image as well as it don't look at the few adjacent pixels. So instead it will look some semi-global values, semi-global pixels. Okay, so it will compute the properties like distance transforms and connected components, which we'll be covering in the last part of this topic. So some types of non-linear filter are listed here. First one is median filter. So median, we know we will sort all the values and will take only the mid value, that is known as median filter. So this we know in statistics. So in case of image processing, the same will be applied. So in median filter, we'll pick the median pixel value from the neighborhood to remove the short noise. It is also known as salt and pepper noise, which means here look at this example. We already know 0 to 255 is a image value. 0 represents 0 to 255 represents RGB color channel values. So 0 represents black and 255 represents white. So the value 200, 255 will be nearer to white, and the value 912 will be nearer to black. So we have certain outliers, right? So black and white are completely contrary to each other. So that is known as short noise. So we'll pick the median pixel value from the neighborhood to remove the short noise. But the problem is it struggle with the Gaussian noise. So this is my input image. I'm going to focus on the center pixel, that is 12. So I have shorted the my input pixel neighborhood is represented like this. So 10, 200, 12, 255, and so, right? So the input pixel value, how we will find the median? So it will be shorted 9, 10, 11, 12, 12, 15, 200, 220, 20, 255. This is the shorted value. After shorting, we'll focus only on the middle value. So the middle value is 12. So the output pixel is 12. So the 12 won't be replaced as some other values, it is 12 only. So instead of an extreme like 255 or 8, the 12 will be replaced. Similarly, if you want to focus on the 10 means either we will perform zero padding or mirror padding and will implement the same value, so which will remove the extreme values such as 8 or 255 will be completely removed and only the median value will be replaced for each pixel. So in this example we have performed the median filter only for the middle value. Similarly, all the pixels will be applied for the median filter and final output image will be completely different, which would be the output of a median filter. So the next one is trimmed mean. It is also known as alpha trimmed mean. So here also we will short the neighborhood values and we will discard certain fraction. Alpha amount of values will be discarded. We will discard the fraction of smallest and largest one before averaging. So consider the same input 10, 200, 12, so and so is considered. Sorted neighbor 8, 9, 10, 12, so and so will be considered. Yes, we'll trim the first smallest and first largest. So 8 and 255 is omitted. The remaining value is kept, and we are taking the average, which is 68. The central value 12 is replaced with 68. So the final output will be instead of 12, 68 will be replaced. So remaining we have to perform the same operation for every pixel. So this one represents 1% of all the values, so that represents the alpha value. If you want to take 2 percentage means I will discard some 2 values from the left and right and will take the average of remaining and pixel values applied here. So this is known as alpha trimmed mean filter. Next one is weighted median or mean. So in this case we'll give more importance to the pixels closest to the center, that is related to robust statistics. So let us take 3 cross 3 block of pixels, 10, 200, 12, 255, 12, 15, 9, 200, 11. So this is the original image represented as 3 cross 3 matrix. So I am going to take a weighted filter, that is 1 to 1, 2, 4 to 1 to 1. Here the center has the highest weight. So the center pixel gets a weight 4 and the direct neighbors, direct neighbors got weight 2 and the diagonal neighbors got weight 1. So the weighted mean means it gives more influence to the pixels closest to the center. If I am focusing on the pixel 12, then the pixel nearer to 12 will have more weights when compared to other elements. That is what mentioned here. So next we have to apply the convolution operation. The original matrix and the weighted matrix will perform convolution. 10 into 1, 200 into 2, 12 into 1. So we'll get some matrix value. Finally we have to add those values, and in order to normalize that we have to divide it with the total weights. Total weights we know 1 to 1, 2, 4 to 1 to 1, sum of all the values, and 1470 divided by 16 we get 92. So this new value is replaced with the central pixel 12. Okay, this is what weighted mean. Okay, what we have done, we have considered the weight filter. So the pixel closest to the center will have highest weight, and we have performed the convolution operation and we have normalized it. So that is the result of the weighted mean. And the next one is bilateral filter. Bilateral filter means it will combine both spatial as well as intensity information. So so far we are seeing only the spatial information. So bilateral it will consider two values, spatial as well as intensity information for edge preserving smoothing. So here look at the same matrix, and I'm going to focus on changing the central pixel 12. The pixel to update is 12 and the neighbor 200 is far in intensity from 12. So the 12 is more similar to black color and 200 is similar to white color. The neighbor again 12 is surrounded with many neighbors, so it is also having the value 11. 11 is very close to 12. So what we will result means the result is closer to 12 will get a high privilege. So we'll focus on intensity information. So the remaining values which are not related, not closer to the central pixel value will have low preference, and those value will be omitted. So my image will look more smoothly. So this is the result of original image. On applying bilateral filtering, I'll get some smoothen values. The next one is iterative or adaptive filtering. So applying filter multiple times will result in cartoonization of images. So when you apply the filter n number of times, the resultant image would be a cartoonization which is used to identify the edges of the image. So the next topic is binary image processing. Binary image means we'll focus only on two colors, usually black and white. That is 0 to represent black and 1 to represent white. Morphological operations can be done in binary image processing. Morphology means studying about shapes in the binary images. So here we'll see some of the morphological operations. Dilation means growing or expanding the images, or we can say growing or expanding the white regions. Okay, so if you have small white dot, dilation make it as a big white blob. So in this case, we have the central pixel 1, remaining neighbors are 0. So central 1 represents white and remaining neighbors represent 0. After dilation, we'll change all this value to 1. So which means the single white dot will be converted to a blob. The next one is erosion. Erosion is nothing but it is the opposite of the dilation. It shrinks the white region. So all the values are 1 here. So except the neighbors, remaining all the white values are considered to 0. So the entire white region is shrinked to small white region. That is the erosion. Opening or closing, it is nothing but the combination of dilation and erosion, which is used for cleaning up the images. So which is used to remove the small holes or objects or smooth shapes. So the next topic is distance transform. So distance transform means it is used to measure the distance from each pixel to the nearest boundary pixels. So we'll see three different types of distance transform here. One is city block distance, next one is Euclidean distance, next one is signed distance transform. In city block distance, we'll focus on Manhattan distance formula, absolute value of x1 minus x2 plus absolute value of y1 minus y2. In Euclidean transform, we'll see root of x1 minus x2 square plus y1 minus y2 square, or we can say root of x2 minus x1 square plus y2 minus y1 square, because we are taking the square and taking the root, so the negative value will be changed. This is applicable to city block distance formula also. In signed distance formula, will indicate the positive value when it is inside the object, will indicate it in negative value if it is outside object. We'll see the examples here. So this is my input image. So I'm having row 2, column 3 as 1, remaining all the values are 0. So the pixel represents 2 comma 3, right? First row, second row and third column. So 2 comma 3 is 1. So in case of city block distance, I'm going to calculate the distance between the pixels. Okay, so distance transform means it is used to measure the distance from each pixel to the nearest boundary pixels. So randomly I'm taking row 4 and column 5. So I'm going to calculate the distance between 2 comma 3 to 4 comma 5. It is getting the value 4. And I'm going to take the distance between 1 comma 1 to 2 comma 3. So 1 minus 2 plus 1 minus 3, I'll get 3. Okay, so these are some of the distance. So when the distance value is high, I can say that my pixel is farthest to the calculated distance. The next one is Euclidean distance. So in Euclidean distance, the same pixel will be considered. The single object pixel is 2 comma 3. I'm going to find the distance between 2 comma 3 to 4 comma 5. So on applying the formula root of x2 minus x1 square plus root of y2 minus y1 square, I will get the distance as 2.33. On applying the same to 1 comma 1, I'm getting 2.24, which means 2 comma 2 comma 3 pixel is at the distance 2.83 to the pixel 4 comma 5, and the pixel 2 comma 3 is at the distance 2.24 to the pixel 1 comma 1. So which means 1 comma 1 is closer to the central pixel 2 comma 3, and 2.83 represents somewhat it is larger than 1 comma 1. So the next one is signed transform. I'm going to find the pixel distance for 2 comma 3. So the distance itself will be 0 for the same pixel. So 4 comma 5, it represents the outside. So the border of the pixels are 0 comma 0, 000, 010 and 010. So which means only these 9 values will get, sorry, 8 values. Apart from 1, we have the border 8 values. Only those values will get a positive value. The remaining will get negative value. The same value but represented as minus, which means it is outside. And if it is in the border means we'll find it as a plus value. So if you calculate the distance between 1 comma 2 and 2 comma 3 using Euclidean distance, you will get some value, but that value is represented as plus. So the plus and minus is used to represent whether the pixel is inside the object or outside the object. The inside represents it is the boundary of the pixel, and the outside represents non-boundary. So some we can use this D1, D2 and signed distance transforms for the applications, alignment, blending and skeletalization. So the next one is connected components. The connected components means we will group the pixel with same label or value into regions. So we'll consider N4 adjacency and N8 adjacency here. It is using OCR, object detection and measuring object properties. So in N4 we'll consider horizontal and vertical neighbors only. In N8 we'll include the diagonals. So this is the example 3 cross 3 image. So in case of N4 connectivity, so look at for the pixel 1 comma 1, look at its up, down, left and right. So there is no neighbor with value 1. Okay, so there is no neighbor with value 1, so it is considered a separate component. Look at the pixel 2 comma 2, look at the horizontal as well as the vertical value. So or both the horizontal and vertical values are 0, so again it will be considered separate component. In case of 3 comma 3, horizontal and vertical components are again no one is found, so it is considered as component 3. So we have 3 components in case of N4 connectivity. We'll consider only 4 neighbors, left, right, top and bottom. In 8 connectivity we will consider the diagonals also, so we have 8 neighbors. So in case of 1 comma 1 we can consider horizontal, vertical as well as diagonal neighbors also. So diagonal neighbors having the value 2 comma 2, for 2 comma 2 we have diagonal neighbors, and for 3 comma 3 also we have diagonal neighbors. So all these three combine into a single component. So the same input pixel, if we apply N4 connectivity we have 3 components. On applying any 8 connectivity adjacency, we get only one component. So this is an example of connected components. That's all. Thank you.